but what I want to emphasize to you is the kinematics of it, how it fits in with all of the what I think of as experimental facts about de Sitter space that we know from quantum theory and curved space-time, and to give you a context and a proper way of thinking about some of those facts about quantum theory and curved space-time that I think are often misinterpreted. So let me begin with that. The first part of this proposal is that the theory of de Sitter space is a quantum theory with a finite number of quantum states, where the exponential of that number, the logarithm of that number, is measured by the Gibbons-Hawking entropy of de Sitter space. That's the strong holographic principle that I told you about last time. But what I'd like to start with is to show you that that principle, which is always stated with reference to a single horizon volume of de Sitter space. This is the Penrose diagram of de Sitter space. It's a square. And the single horizon volume is this little triangle in the corner. And if you think about the geometry at very late times, de Sitter space is a sphere that starts out infinite in the past, shrinks into some finite volume, and then becomes infinite in the future again. The region that's covered by this causal diamond has a finite size, and at very late times, it seems like a very tiny fraction going to zero of the total de Sitter space. And this people often find confusing. And your temptation when you see a geometry like this is to say, well, let's think about it far in the past when there's a huge sphere. So, okay, there's a cosmological constant, space is expanding exponentially, or in that region contracting exponentially. But nonetheless, let's try to think about putting particles into this system, and it looks like you can put an awful lot of particles into this system. And that gives you the impression that de Sitter space actually has an infinite number of states associated with it. But the proper way in a theory of gravitation of thinking about what a quantum theory consists of in terms of classical solutions is you have to think about classical solutions that satisfy appropriate boundary conditions. And in this case, I would claim the appropriate boundary conditions is that the space be asymptotically de Sitter in the past and in the future. And if you do that, you realize that most of those states you make by throwing things in from infinity are going to lead to disaster. Because if you throw particles in from infinity and space is contracting around you, the particles are shoved together, and most of those states are going to form huge black holes. And you can sort of count how much by using the black hole entropy formula. So if you throw in a certain entropy of quantum states, a certain set of quantum states that live in a subspace of very high entropy, and you throw them in such a way that all of their energy gets concentrated in some small region, a black hole is going to form, because that's the most common state that you can get at that level of energy in that volume. And if the black hole radius is too big, black hole areas don't shrink, and so the black hole has a singularity inside it, but now there's a competition because space around you is shrinking down the cosmological solution. And so at a certain point, you've thrown in so much stuff that the black hole horizon is bigger than the throat that de Sitter space wants to push itself through. And there's a contradiction, and instead you get a singularity. And again, these are just words, but a number of people, Gary Horowitz in particular, have studied this. And indeed, this is what happens when you try to perturb de Sitter space by what seems like innocuous perturbations out in the past. So if I think about generic configurations in flat space and generic configurations put those generic configurations into the past of de Sitter space, I won't get the future of de Sitter space. And so this is an argument directly in this global coordinate system, which doesn't, covers the whole space, that the number of states in the theory defined as the set of all solutions that you can think of that'll be asymptotically de Sitter in the past and the future is finite. Yeah.
What about small black holes? Would those still count as asymptotically de Sitter if they don't evaporate?
But they do evaporate.
So you say I can't cook up one hole?
No. Well, you can cook up charged. You can cook up charged black holes that, depending on the spectrum of magnetic monopoles, maybe won't evaporate. Very uncommon. You can get one. If you try to make one that's too big, you'll.
Small already changes the future infinity.
It doesn't change the future infinity in any significant way. It's in a localized region. Yeah. I mean, a black hole in Minkowski space, if you think about general relativity, black hole doesn't decay. It changes future infinity. But we still consider that to be asymptotically flat. So some localized disturbance like that, I think one should consider to be asymptotically de Sitter, even if it's stable. And classically, it will be stable. Well, I don't think there's a good definition of what asymptotically de Sitter is mathematically, if you want to be completely, okay. It's all of these asymptotically X definitions you have to be really careful about. And up until ADS-CFT, we would have gotten it totally wrong in ADS space. So I'm a little bit leery about making pronouncements about what asymptotically de Sitter means until we have a quantum theory. Okay, so that's point number one. So from now on, I'm going to concentrate without apology on the static coordinate system, but what I do want to emphasize to you is that in fact, in the static coordinate system, you've got all of the states that you have in the global coordinate system. So you say, oh my gosh, if I look far in the future, there are all of these horizon volumes. Stuff, if I think about it from a global perspective, stuff goes outside my cosmological horizon and it gets lost. I can't make a theory of just the single static patch. This is false, and it's just as false here as it is in black hole physics. The time of this static patch is a hyperbolic angle that goes from here to here as t goes from minus infinity to infinity. So if you look in the time coordinate of that static patch, just as in a Schwarzschild black hole, if you use Schwarzschild time, nothing ever falls through the horizon. So where are all of these states that went through the horizon from the global point of view? Where they are is right up against the horizon. If you look and solve, if you work in quantum field theory and curved space-time, and try to look in the global coordinates at the wave functions of all possible states that have low energy as measured by the observer at the horizon, then what happens is the following. Here's the metric in the static coordinates where f of r is given by this function over here with m equals 0. The m not equals 0 solution is the black hole in de Sitter space. M equals 0 is empty de Sitter space. If I look at this, f of r goes to 0, just like in a black hole solution. And near 0, what's really happening is that that boundary near r equals capital R, where f of r goes to 0, that boundary is becoming null. The metric really looks like this. And if you look at the solutions of the Klein-Gordon equation, the Dirac equation, whatever you like, in this coordinate system, and you look at how many states you have that have low energy as measured according to this Hamiltonian by an observer sitting at the origin of these coordinates, this observer that defines the static patch, who goes up along that time-like trajectory, you find that those states have very, very low energy. This is the famous redshift. You know that when you throw something into a horizon, what happens, if it's sending signals back out to you, is not that the signals don't get to you, but that they get redshifted. So there are, in fact, solving quantum field theory in a static patch, in addition to particles propagating in the bulk of de Sitter space and able to get back to you, there are an infinite number of states of quantum field theory that correspond to things pasted up against the horizon that have arbitrarily low energy. Those states are the mirror in this coordinate system of the states that in the global coordinates went outside the horizon. So they're there in the static patch to be talked about. The real question is their number infinite or not? Okay? Now, I've just given you an argument in the global coordinates that their number is not infinite. In the static patch, there's this rather sharper argument, based, of course, on a conjecture, that the static patch has a finite area holographic screen, and so the total entropy of the system is finite. So that is the picture that I'm going to be promulgating to you today. And it's going to be very important to separate out those states that are near the horizon from those states that can look like particles propagating to the static observer. And what we're going to find is that in order to describe that situation, we need two different Hamiltonians. And just as a bit of motivation for these two different Hamiltonians, I want to tell you a little story about what the horizon looks like. So as I said, the metric of de Sitter space near the cosmological horizon looks like this, with appropriately defined coordinates. De Sitter space, this is the radius of curvature of de Sitter space, and if we were interested in taking the limit towards Minkowski space, this R would be going to infinity. Now, for comparison, this is a causal diamond. In Minkowski space, there's another diamond, which is the entire space-time. The Penrose diagram of Minkowski space is a diamond. And when you take the limit as the de Sitter radius goes to infinity, what approaches Minkowski space is not all of de Sitter space, but a single causal diamond, a single observer's causal diamond. And so we should be comparing this metric to that metric near the horizon, because in holographic theories, null surfaces like the horizon are the places we should be looking for our degrees of freedom. And this is what Minkowski space looks like. It's the same metric, but instead of being multiplied by this large fixed R squared, it's multiplied by 1 over V squared, and V going to 0, which is the null surface that defines the horizon, is becoming singular. This is just the statement that the Minkowski causal diamond is really infinite in size. If we want to make a theory there, we have to do an infinite conformal rescaling. The resulting theory had better be also invariant under finite conformal transformations, and the finite conformal transformations of the holographic screen are precisely the Lorentz group. So the comparison between these two formulas leads me to ask questions about how various generators act on those coordinates. And so it's very standard in Minkowski space. If you look at this metric, you can ask, well, this is the causal diamond of some particular observer. That causal diamond, because I picked a rest frame, so there's some observer. I can go to another one by doing a conformal transformation on this, but I've picked a particular one. And in that rest frame, the generator that I call the Minkowski energy is d by du. That's how it acts on the horizon coordinates. Now I can ask, how does the generator of time translation and static tau act on the horizon coordinates of the de Sitter horizon, and it acts like that. And so this is not that. There's a statement we always make that the de Sitter group contracts to the Poincare group. That's defining generators in a way that you really shouldn't be doing in Minkowski space, but does make sense in quantum field theory. I'm sorry, in quantum gravity you shouldn't be doing it, but in quantum field theory in fixed curved space-time background it does make sense. When I ask about the action of some isometry of a fixed metric, I can ask about its action on some finite point in the metric or someplace out near some extreme region. If I ask about the action of the static de Sitter time translation right at the origin of the observer that defines the static coordinate system, then indeed, as the de Sitter radius goes to infinity, it approaches the Poincare Hamiltonian P0. But now we're asking a different question. We're asking how these generators, which are vector fields in space-time, and they vary over the space-time, they act differently in different places. And on the horizon, the two generators act differently. So they're two different generators. They don't commute with each other. That's the picture that I'm going to take over to the quantum theory. And now you can direct your eyes upwards to the slides. This is the picture which I claim, and I'll explain this to you, leads to our standard the facts, experimental facts about de Sitter space, where by experiment I mean the theoretical papers of Gibbons and Hawking and all those who followed them. Let's assume there are these two Hamiltonians, that the Hilbert space is finite dimensional, and that the first Hamiltonian H is really describing all of these states up against the horizon in de Sitter space, which have very, very low energy. Well, instead of saying that they all have exactly low energy, which that seems to be what happens as you approach the horizon exactly, we're dealing with a quantum theory. Classical notions like that will get disturbed a little bit. So there's a characteristic energy scale in de Sitter space, 1 over r. The de Sitter temperature is 1 over 2 pi r. Okay? And I'm going to insist that this first Hamiltonian, the static Hamiltonian, describes the states near the horizon as a system with an energy bound which is of order 1 over r. It's a Hamiltonian in a finite number of dimensions, so I'm saying its maximal eigenvalue is of order 1 over r. But the Hilbert space has dimension e to the a. And so the typical energy splitting in this Hamiltonian is e to the minus a times 1 over r. In other words, it's got this incredibly, incredibly dense spectrum of levels packed into a tiny little interval, which in the classical limit squeezes down to 0. Yep? That's in fact true. I think that the consequence of that for the real theory will be that for any measurement we will ever do in this theory, we'll never be able to determine exactly what this Hamiltonian is, and we'll need to know certain features of it, and I'm going to tell you about those features. No, ADS is a mathematical theory. Everything is... Yeah. Right. Exactly. Exactly. So the bottom line you're anticipating is that the theory of de Sitter space is going to be not unique. But that not uniqueness will affect nothing that we could ever possibly, in principle, actually measure. And the reason for that is that as we'll see, the number of states in this theory that we can actually access by local measurements is vastly smaller than the total number of states. Most of the states are just there to provide a heat bath in which the localized states propagate. So the time scales for propagation, according to this static Hamiltonian, range from R, which is if we take this to be the realistic radius of the universe according to our current cosmological measurements, R is roughly the age of the universe now. So that's the shortest time scale on which H allows something to vary. And then we go out to long time scales of order, the so-called recurrence time, e to the area over 4L Planck squared times R. That's the recurrence time. Because of what Joe just said, physics on that recurrence time is totally silly. It's not something that we will ever measure. It's not something we should really be thinking about in making a theory of this. The time scales that localized observers can measure are much, much shorter than that, so much shorter that it doesn't matter what units you measure them in. Okay. So where are we? Now, the Poincaré Hamiltonian, this little cartoon of it suggests that it doesn't commute with H. But what I think we want is a quantum formula that says that the commutator of H with P naught goes like this. If the function f is linearized around P naught equals 0, this gives a formula with a 1 over r in it, which if I normalized H to have energies of order 1 over r, that's what we would expect from here. And what I've put in over here, the maximum, the order 1 values for this function, is the so-called Narii black hole mass. What's the Narii black hole mass? Well, remember I told you one of the clues to what quantum gravity is doing is that the high energy spectrum is dominated by black holes. So we can think about black holes in de Sitter space, and in order to do that, all we have to do is put the Newton potential into the metric. This is this miracle of the black hole solutions of any gravity theory. This is what the equation looks like. If you look at the zeros of f of r, you see this is a cubic equation, and it has two positive zeros, r plus and r minus. The third root of the equation is negative and is equal to r plus r minus. That's because when I multiply up this cubic, one of the terms is missing, and you can just see that that's the one that corresponds to the sum of all of the eigenvalues. And these two are interpreted as well. A black hole has a horizon. De Sitter space without the black hole has a horizon. So if I put a little black hole into de Sitter space, I should expect to see two horizons. And that's what these are, but there's some really interesting algebra you can do. And what you can show is that the area of the sum of the two horizons of the black hole is less than the area of empty de Sitter space. Okay? The conclusion you should take from that is that any localized excitation of de Sitter space is a low entropy excitation. De Sitter space wants to be what I talked about up here. Namely, I've got this Hamiltonian H. It's got, it's a Hamiltonian that has ergodic dynamics. One way to get such a Hamiltonian is take just about any random distribution of Hamiltonians you want and pick a typical member of a random distribution. These are the Hamiltonians for which Michael Berry, Mark Srednicki, and others have actually been able to prove ergodicity. And so typical Hamiltonians will have a chaotic spectrum, which leads to chaotic time variation. And that's what we're choosing H to be. Now you start out in any state you like and evolve with the Hamiltonian like that, and you find that after a short relaxation time, you end up with results that are indistinguishable from the infinite temperature thermal ensemble if I started from a random initial state. And so that's what de Sitter space typically wants to be. It wants to be a typical state in the Hilbert space, and that is what it would get to if I started with any initial state and let H run for enough time. Now, the time scales for that to happen are long, okay? But what I see is that localized states corresponding to black holes are decreasing that entropy. So they're doing something special, okay? We happen to be localized people. I don't see anybody here who's spread over the horizon of de Sitter space. So we're nonetheless interested in these rather improbable occurrences, these localized things that are going on. And we're also interested for our own personal reasons in timescales that are shorter than the age of the universe. And so we'd like some description of physics that goes on timescales shorter than the age of the universe. So that's what the Poincare Hamiltonian is supposed to do. It's supposed to describe the physics of the localized states in the horizon volume. It's not most of the states in de Sitter space. We'll do the counting in a little bit. And that's the Hamiltonian that we care about. That's the one that's going to have the electron mass and the proton mass and your mass in it as not exactly eigenvalues in your case, but you know the masses of very long-lived metastable states. That Hamiltonian doesn't commute with H, but when I forgot to tell you, if I solve this equation and look at what happens, you know how cubic equations change as I change the parameters. I told you I've got these two horizons, both of which have area less than the total de Sitter horizon. Now as I bump up the black hole mass, the black hole horizon grows, the cosmological horizon shrinks. There's obviously a point in the middle where they meet. That's the so-called Narii black hole. It's the maximal mass any black hole can have in de Sitter space. So another argument that the theory is a theory with a finite number of states. You try to put in as much energy as you can, and you can't. You stop at some certain point. The spectrum of the Hamiltonian, we'll see that's properly interpreted as the spectrum of P0, is bounded, and it's bounded by this number. So what I'm saying is that when P0's eigenvalue is much less than its bound, the commutator of H with P0 is very small. The commutator of H with P0 is very small means that P0 eigenstates will be approximately stable under H evolution. And since H eigenstates have this incredible degeneracy, P0 eigenstates will split that degeneracy in an appropriate way. Yeah?
P0 an element of the de Sitter group?
Absolutely not. Okay. P0 is an element of what will be the emergent Poincare group. Okay. The de Sitter group is largely irrelevant to the theory of de Sitter space because it's a purely mathematical thing. The single observer's horizon volume is not invariant under most of the de Sitter transformations. The subgroup that fixes the static patch, you might want to, because of my cartoon motivation, you might want to think of my Hamiltonian H as being the generator of these time translations in tau. Whenever I say that to Don Maralf, he yells at me. And so I don't want to say that at this point. You'll also see, if I get to it, there are rotations on this sphere in the static patch, which we'll use a lot. But those rotations are not the same as the rotations that end up being rotation invariants in the Poincare invariant limit. So I'm not sure what they're good for. The real physics of de Sitter space, in my opinion, will be the physics of the localized states and will involve a sort of approximate scattering matrix for those localized states. And the de Sitter group has absolutely no relevance for any of that physics. It may be that mathematically you can put in a Q-deformed version of the de Sitter group into this formalism. And I've thought about that. David Lowe has thought about it. But I don't think it's terribly important. Okay? What's really important is figuring out the physics that we're actually going to measure, not the physics of this Hamiltonian that mostly describes states that we can never access. Okay. So now there's a really fantastically interesting formula that follows when I look at the black hole and I look at the entropy deficit of the black hole. I just told you the black hole has a mass, has an entropy, including both its cosmological and black hole horizons, which is smaller than the entropy of de Sitter space. And so I can think about what the difference is. And here's the formula for the difference in terms of these quantities, R plus and R minus. I'll give you a homework assignment to figure out what R plus and R minus are in terms of the mass and the de Sitter radius and the Planck mass. But what you find is that this is the entropy deficit. It's just that. And then 2m, I've solved half your homework problem here, is given by this formula in terms of R plus and R minus. And if you look at that formula for small r minus, so these are black holes that are much smaller than the Narii hole. We're not too interested in Narii black holes because that's a black hole that spreads across the whole universe. Very low entropy state from the point of view of de Sitter space, and not one that we'd care to visit. So if I look at small r minus is the Schwarzschild radius of the black hole horizon, you can approximate this formula, and you get that the entropy deficit is 2 pi r times the mass. That's really lovely, because that means is that what that means is that if I look in the infinite temperature thermal ensemble for the Hamiltonian H, the probability of finding a state of mass m is e to the minus 2 pi r times m. And that's the thermal formula for the de Sitter temperature that we usually derive from quantum field theory in curved space-time. Okay. And so that formula is something that tells us something about the spectrum of the Hamiltonian P naught. It says that the degeneracy of the eigenstate of the Hamiltonian P naught, which has eigenvalue m, is smaller than the total Hilbert space by this amount. Okay? And so the relation between H and P naught that has to be satisfied, this is compatible with a commutation relation like this, but we learn a little bit more about the relation between them in this way. And if I get to it, I'll show you a model of a Hamiltonian that does this for a model of what the black hole spectrum is. I'm not sure I'm going to get to that. Of course, I don't have a model of the de Sitter Hamiltonian that includes the really low eigenvalues, like the electron mass, but I'm working on it. So the Gibbons-Hawking result was always a little peculiar because it was a system at finite temperature, but somehow you couldn't change that temperature. It was fixed. It was unique. What was funny, what was unique about that temperature? Well, from this point of view, the reason it's unique is because we picked a typical state in the whole Hilbert space and just let the Hamiltonian H act on it for a long enough time, and then we got a thermal state which was infinite temperature from the point of view of H. And what this is saying is that from the point of view of P naught, it's a fixed finite temperature, 1 over 2 pi r. Okay? So that's what a quantum model of de Sitter space should look like. So this model, I haven't put a lot of meat on the bones yet of this model, but just these crude ideas already explains the most striking feature of quantum field theory in de Sitter space. I've also explained to you previously how a model like this could explain the Coleman-de Lucia tunneling probabilities for de Sitter space if our model of the low energy effective Lagrangian that corresponds to de Sitter space is above the Great Divide. Then this model automatically explains the biggest factor in the Coleman-de Lucia tunneling probability, and the one that's independent of the details of what the low energy effective field theory is, as long as it's above the Great Divide. There's also another calculation that was done long ago by Ginsburg and Perry, and then investigated further by Busso and Hawking, which is what's the probability of spontaneously nucleating a black hole in de Sitter space. So they figured out an instanton for that. And that instanton also satisfies this formula. You might not be surprised by that. It better be if de Sitter space is really thermal, but it gives you exactly the same result as this formula. So it says that the probability is thermal with a temperature 1 over 2 pi r. Now, at this point, you don't understand this part. So in order to help you understand that part, let me go on and talk about particles in de Sitter space. So this is a little calculation. It mirrors calculations people have done in black hole physics, and I think it's really important in general for trying to understand where particle states come from in quantum gravity. And so you do the following thing. You say, okay, I have a certain region of space of size r. I'm not going to worry about the difference between the de Sitter metric and the Minkowski metric for this, because up near the horizon of the static patch, where they're drastically different from each other, anyway, I know that the correct description of the states is not in terms of normal particles propagating in de Sitter space. When I solve field theory, I find this infinite set of states plastered to the horizon. The holographic principle tells me to cut off that infinity. I have to describe that in a non-field theoretic way. But the states kind of in the bulk of de Sitter space, you should expect to be able to describe in terms of field theory. So how do I do that? Well, I want to see how much entropy there is in such states. So I say, if I look at field theory, how do I get a lot of entropy? You get a lot of entropy by going to the UV. In field theory, if you have a region R, you have an ultraviolet cutoff lambda, you get an entropy lambda cubed r cubed times some number. That's because field theory at high energies is approximately scale invariant. That's what you get. But now we know in the theory of gravity that the description of most of those states is wrong if the size r is big enough, because the Schwarzschild radius corresponding to this is lambda to the fourth. The mass is lambda to the fourth r cubed. And the mass and the Schwarzschild radius are the same thing in Planck units in 4 dimensions. So I have to insist that this radius r be bigger than the Schwarzschild radius. But because the Schwarzschild radius grows like r cubed for fixed lambda, I can only do that by making lambda smaller as I make r bigger. That sounds really crazy. And in field theory, it is really crazy. You don't want to put an ultraviolet cutoff on your theory that scales like 1 over the radius of the universe. That is, however, the way to correctly estimate the maximal entropy in field theoretic in particle states that you can put into a region R. I will in a minute show you a formalism that gets this counting right without making this stupid mistake of putting a universal ultraviolet cutoff that doesn't allow you to have particle masses bigger than the... But let's suppose we do that. Okay. Then you put these things in. This is the Schwarzschild radius. You say r less than r Schwarzschild. It's a little calculation I urge you to do for yourselves. You find that the entropy in localized states, okay, scales like Rm Planck, not squared like the entropy of de Sitter space, but Rm Planck to the 3/2. So the localized particle states in a single horizon volume have an entropy which is down by a factor of Rm Planck to the 1/2. Now remember, the number of states is the exponential of the entropy. So the states that you could possibly ever localize are so small in number compared to the total that they're totally negligible. Okay, for the real world, these numbers are like e to the 10 to the 123 compared to e to the 10 to the 90. Okay, now both of those are really large numbers, but the first one is really a lot bigger. And you can say all kinds of amusing things about differences like that. What is really at issue here is that these are the only states out of which we can possibly imagine some future advanced civilization making measuring devices. We can't do anything like that. You know, we can sort of make measuring devices that have e to the 10 to the 20-something states. Okay, or if you go to SLAC, you can bump that up by an order of magnitude or something. But we're really just not in the right ballpark for this. But even if we did the best we can possibly do with localized measurements, there's no way that we could ever gain information about this system. Remember, a measuring apparatus always has to have many more states than the system it's measuring, because we want its quantum fluctuations to be negligible over the time that we measure the quantum fluctuations of the system. So it's totally ridiculous to ever think about the detailed physics of the horizon states. It makes no sense at all. No, it's one of these things that it makes no sense for all practical purposes, so much that it's for all purposes in principle. Okay? So our theory, because of this, our detailed mathematical quantum theory of de Sitter space will have to have some ambiguity in it. And that, I claim, is the details of the Hamiltonian H. The details of the Hamiltonian H will never be measurable by anyone. Therefore, our theory, we can write down many different theories with different Hamiltonians H. If I look over periods of order recurrence time, the details of the Hamiltonian H matter. And there are these silly problems that people call Boltzmann's brains that happen over periods of order recurrence time. And different choices of the Hamiltonian for de Sitter space will make different predictions for how often Boltzmann versus Einstein gets spontaneously created over many recurrence times in de Sitter space. It's just not physics. And you shouldn't be worrying about it. You shouldn't be thinking about it. Okay. So I'm sorry for those of you who never worried about those problems that I even mentioned it. But there are people who do think about it. The other thing that's really interesting about this formula is that it gives me now a correctly quantum mechanically regularized picture of the infinity of states that we're talking about. If localized states only have entropy Rm Planck to the 3/2, then I can make Rm Planck to the 1/2 commuting copies of whatever my theory is of the localized states. That, I claim, is what you're getting when you do quantum field theory in curved space-time in global coordinates and pay attention to independent localized degrees of freedom in each horizon volume. You say there are an infinite number of horizon volumes, and that each of those horizon volumes could have an infinite number of states. You're wrong on both counts, but you're wrong in counting horizon volumes only to the extent that Rm Planck to the 1/2 is not infinity. Rm Planck to the 1/2 is, for the real world, is about 10 to the 30th. Okay? So it's a fairly good approximation for many purposes to consider it equal to infinity. Okay. Now let me show you a real formalism that does this counting correctly. Now I want to take you back to what I was talking about last time, talking about spinor bundles over fuzzy spaces. Okay? So what are we doing here? We're doing some four-dimensional compactification of another theory, okay, of a theory in higher dimensions. And so my space has a holographic screen that extends into the higher compact dimensions, and it's got a two-sphere in de Sitter space. Let me first tell you about the fuzzy two-sphere, because this is mathematics that all of you know very well. So if I think about the two-sphere is described completely by its algebra of functions, and we know that we can expand those functions into an infinite power series in spherical harmonics. Remember also that a spherical harmonic is a representation of SU2 or SO3, which has some dimension n. And that there are representations with all possible integer dimensions, if I include both half-integral and integral dimensions. And so if I look at n by n matrices, these things have two properties. Number one, they form a closed algebra. M1 times M2 is another n by n matrix. It's not a commutative algebra, but it's a nice associative algebra. And secondly, if I think about the n, okay, M is a matrix, Mij. This takes on n values. This takes on n values. If I think of these n values as the n-dimensional representation of SU2, then M transforms as the tensor product of two n-dimensional representations of SU2. And you all know the Clebsch-Gordon series for SU2. It gives me all possible angular momenta, integers, between 0 and some maximum. Okay? So writing down the algebra of n by n matrices is a way of approximating a space whose basis is all spherical harmonics. As I take n to infinity, I get more and more spherical harmonics. Furthermore, if I take the generators, the n-dimensional generators of SU2, and divide them by square root of n, okay, I get generators which, as n goes to infinity, commute with each other, and they square to 1. So let's call these things n super a. The sum of the n super a's squared equals 1. And they commute in the n goes to infinity limit. And the spherical harmonics, as you know, you can think about if I want to break the space of all n by n matrices up into SU2 representations, the way I do it is I take the generators, okay, and I have the matrix 1, which is a singlet. I have the generators, which are the vector representation, and then I take products of the generators, and because of the commutation relations, they're just symmetrized products, and because the squares sum to the Casimir operator, they're symmetrized traceless products, and that's why you get spherical harmonics. And you're getting all of them in the limit, and these things commute with each other, and so you get the sphere back in the limit. Now, mathematicians would like to dress up this argument a little bit, but it's basically a correct argument. This is a way of approximating the two-sphere. It's called the fuzzy two-sphere. The spinor bundle over the fuzzy two-sphere breaks up into two chiral parts, psi IA, psi dagger JB, and these are n times n plus 1 and n plus 1 times n matrices. They have, again, by the rules of angular momentum addition, all half-integer angular momenta up to some maximum. And these things converge in the limit as n goes to infinity to the spinor bundle over, so if I look at all possible such matrices, they form a module over the algebra that I've defined in the limit, which is the algebra of functions on the sphere, and it's the spinor bundle over the sphere. So this is the way that you can think about, in a rotation invariant way, cutting off the sphere. Now, how does this lead to particles? And it leads to particles in a way that any such non-commutative construction naturally leads to particles. And the way that it does is like this. I've done this, and I've done this once. But once I've done it once, you can't prevent me from doing it again. And so I can take an algebra, which is n1 by n1 matrices here, block n2, and so on, down to nk. And in each of these blocks, I can take the same limit where the ni's go to infinity with ni over nj fixed. Okay? And then, because of the nature of matrices, if I think of this as an algebra, it's just the direct sum of a bunch of copies of the previous algebra. But when I write them as matrices, there's an issue of permutations, which one I put first. And that's just a gauge symmetry. That is to say, which block is on top doesn't matter. And so the theory of matrices, of taking block diagonal matrices or things that commute in blocks and replacing them by block diagonal matrices, introduces a gauge principle of the permutation symmetry. That principle is interpreted and has been interpreted in many contexts in theoretical physics, rather particularly in so-called matrix theory, which my colleagues and I proposed for a description of M theory that was non-perturbative and quantum mechanical. That is treated as particle statistics. So you have a gauge symmetry under the permutation group. Particle statistics is nothing but a gauge symmetry under the permutation group. And furthermore, using that minus 1 to the n that I showed you last time, and using the fact that that turns the half-integer spin things into things that anti-commute rather than commute, if I put this together and take the construction, you remember last time I got the supersymmetry generators, the degrees of freedom of a massless particle going out a certain point through a certain point on the sphere. The way I would do that actually, the way I would make that approximation is by starting with these objects and taking this n goes to infinity limit that I'm talking about. Then the half-integer things anti-commute, and that leads to the proper Fermi statistics when you make this construction of matrices. And so this is a way in which particle physics comes out of this holographic formalism. And particle physics comes out in a way that is automatically supersymmetric. You always get particles that always get superparticles, not particles, in the n goes to infinity limit. And furthermore, you kind of restricted your attention to block diagonal matrices. Now, I could just do that by fiat, but there's a good reason not to do that in de Sitter space. And the reason is the following. Suppose I take a construction like this, and suppose the total n of this space is finite. Okay? So the sum of ni equals to some fixed total n. Now, one of the peculiar features of this is that I can make these ni's different from each other. But if I have a constraint like this, then the sum of the ni's being equal to n means I can't make this one big without making this one small, and vice versa. There's a complicated mutual constraint on the n values of these different particles. What do these n values turn into? Well, notice that in the limit, I get a whole bunch of continuous ratios from these n values. What does that continuous quantum number turn into? I showed you last time how I got the supersymmetry algebra, but there was actually something missing. When I computed in my little cartoon of the calculation that I would do here, Q alpha, Q beta dot, I got sigma mu alpha beta dot, and then I got something I called the momentum, which was a unit vector, a null vector that was going out through a particular unit vector on the two-sphere. But I didn't get the overall scale of the momentum that's going out. These ni's, if you go through the construction, become the pi's. So if I go through this construction for all of these simultaneously and take the limit, I find SUSY commutation relations which close on the SUSY algebra of a whole bunch of particles with a separate pi for each particle, with that pi being the limit after some infinite renormalization of the n of the block. Okay? So what this says is that the description of particles in de Sitter space is done as follows. The total number of blocks is telling me something about the total number of variables. I'm actually going to count all of the matrices, not just the block diagonal ones. And so these are fermionic-like objects. They actually have more complicated commutation relations, which I hope I'll get time to mention in a minute. But they have some finite dimensional algebra. And so when I look at objects like this that fill up a whole n by n plus 1 matrix, I get an entropy that scales like n squared times the logarithm of the dimension of the algebra that the size generate, or the dimension of the representation of the algebra that the size generate. That square is to be, therefore, identified up to constants with Rm Planck squared in de Sitter space, because that's what I expect the de Sitter entropy to scale like. So this construction gives me a natural description of the de Sitter entropy in terms of n by n plus 1 fermionic matrices with some finite dimensional algebra. And I'll explain to you what this D has to do with in just a minute. So when I do this, what I've said is I get, in the limit, if I take n to infinity, each of the ni's can also go to infinity at fixed ratio, and I get an infinite number of particles with arbitrary values of their longitudinal momentum. However, if the de Sitter radius is finite, this system can only describe a finite number of particles, and how many particles it can describe depends on how much longitudinal momentum I give to each particle. So if I have two particles of huge longitudinal momentum, can't put any more in and still satisfy this constraint. So now you want to ask the question, suppose I try to maximize the entropy of these particle-like states, which, with the constraint that they still behaved in a particle-like way. Well, what do they need to do to behave in a particle-like way? First of all, I have to be able to make lots of them. So I want to have lots of blocks. That means I should try to take the ends small. But if I take the ends really small, then they don't behave like particles because they don't have very many spherical harmonics, and they can't be localized into a direction on the two-sphere. And so you can ask, what do I do to compromise? How do I maximize the entropy in such a way that when n is large but finite, I get rather localizable states that still have a lot of particles around, so I can really think of this as a good approximation to what I would get in Minkowski space. The answer is you maximize the entropy by taking ni to scale like the square root of n. Then you can have lots of spherical harmonics per block and lots of blocks. And if I do that, I get an entropy that scales like n to the 3/2, like the particle entropy in the calculation that I waved my hands about before. Here, that calculation is rigorous, and secondly, it doesn't restrict the longitudinal momentum to be too small, because I can describe lots of particles, or I can describe a few particles with lots of longitudinal momentum. This formalism has a flexibility that quantum field theory with a cutoff doesn't have. Quantum field theory forces you to cut off the momentum of all the particles by the same amount. This formalism allows you to cut off the momentum, and naturally cuts off the momentum of any given particle, depending on how many other ones are around. Now you can also see how the formalism has in it all of the rest of the horizon volumes of de Sitter space. Because consider this first off-diagonal block, adding in the one in the lower left-hand corner so that it has the same number of blocks as this thing over here. That's another copy. If I take, again, ni of order square root of n, I get another copy of that from this off-diagonal, and another copy, and another copy, and another copy. Each time I take all of the things that are k times off the diagonal here, plus what's k steps over from here. This discrete transformation, by the way, might be some discretized de Sitter boost that changes from horizon volume to horizon volume. And so I can describe the other horizon volumes n to the 1/2 in number in terms of the off-diagonal blocks of this matrix. Okay. So I think I don't have a lot of time left. There are two other things that I would have liked to have shown you. One is how you can understand the entropies of black holes in this formalism. But I think more importantly, I want to talk about compactification. So first of all, why do I need compactification at all? So the paper where this formalism is sketched out is a paper I wrote with Tomeo Fiol and Alex Maurice. And there we tried to do this without compactification. And we came to what was a very interesting, possibly at the time sad result, but actually interesting result. You can take the limit of this formalism without compactification, and if you insist on doing it, you find that you do get a spectrum of massless supersymmetric particles coming out in the limit. But it's a chiral multiplet. There's no graviton. It was supposed to be a holographic theory. Where's the graviton? And so we just sent that paper out, thought some more. There's an obvious idea for where the graviton comes from. Namely, if you remember I told you, we know very well if we have 16 operators with the commutation relations that interpreted as the spinor of SO9, this gives you the supergravity multiplet in 11 dimensions. And there's a familiar supersymmetric helicity counting that tells you that you need 16 real generators if you want to be forced to have a spin 2 particle in the spectrum. And so what that suggests is that to get a decent theory of de Sitter space in 4 dimensions, you're going to have to add in degrees of freedom that correspond to compactified dimensions. And this formalism sort of tells you how to do it. You should take your matrices psi IA to have another, let me call it an index, M, okay, where this index really means a whole new matrix space, because what this index M is indexing is the spinor bundle over the compact space. Okay? So these will have anti-commutation relations psi IAM, psi dagger JB N equals delta IJ delta AB times some ZMNs. And the ZMNs and the psi's have to close on a superalgebra, which in the limit gives rise to particles that live on some compactified space. So I'm going to treat the compactified space in the same way that I've treated the two-sphere. The theory of fuzzy geometry for general compact spaces is only partially worked out. It's very, very well known for Kahler manifolds. For Kahler manifolds, the way that you do it is you look at holomorphic line bundles over the Kahler manifold. Those are always finite dimensional. And you can take sequences of holomorphic line bundles over the Kahler manifold, and the algebra of matrices in those Hilbert spaces converge for many, many different sequences to the space of functions on Kahler manifolds. And this is a construction, I believe, that was first made by Berezin. So there's a rich literature on this. And what one has to do is to do it in general. Now, however, I want to point out something interesting about this construction. This algebra for one of those fuzzy Kahler manifolds will have some fixed finite dimension. Its smallest representation will have a log D. The way that should be interpreted is the following. If I think in Kaluza-Klein compactification, okay, the entropy of de Sitter space is proportional to the radius of de Sitter space squared in 4-dimensional Planck units. Okay? But the 4-dimensional Planck scale is gotten from the higher dimensional Planck scale by the following formula. This is equal to the volume of the compactified manifold in MD units, however many dimensions you've compactified. And this is LD. So this is times MD. You saw this formula in Miriam's lectures, for example. And so the way you should interpret this formula here is we have a total entropy. This integer n scales like the radius of de Sitter space, scales like, but it's not the radius of de Sitter space in 4-dimensional Planck units. And the correction is this log D is equal to that. Now, the integer n, okay, is really to be thought of as the ni for each of these. No, I'm sorry. I didn't say that correctly. So the entropy of de Sitter space is given by this formula. Okay. This is a number we know from observation. If you believe the holographic principle, this number is determined in terms of our cosmological horizon, which we've measured by measuring the cosmological constant. So this is a fixed number. Pi times this is 10 to the 123rd. In this formula, I can't both make n and log d large. So this formula, if I want n to be a large number, in order to have a nice particle interpretation for the formalism, then the volume of the compact dimensions can't be too big. And for example, in this formalism, it would make no sense whatever to have ADD type large compact dimensions. They just don't give you enough entropy for particle states to have enough degrees of freedom to behave like particles. Second point is, once I've established that, so that the volume of this compact space, which is the dimension of this representation, is finite, then I have shown you that there are no moduli that can take on continuous values that characterize this compactification. And this is pure kinematics. Why can't there be moduli? A fuzzy space, which is a finite dimensional representation of a non-abelian algebra, a fuzzy space does not have continuous moduli. In the construction of fuzzy kahler manifolds, for example, the moduli of the kahler manifolds come about from the different ways one can take the limit in the spaces of holomorphic line bundles. So the classification of holomorphic line bundles is given by the Picard group, which has to do with the integrals of U1 gauge bundles over 2 cycles. And it's telling you something about, in the limit, about the relative sizes of different 2 cycles in the manifold. So the moduli of Calabi-Yau manifolds, or any Kahler manifold, in fuzzy compactification only appear in the limit where you take the fuzziness away. Any step away from that, and it's discrete. And if I tell you that the maximum dimension of this representation is in fact bounded by experiment, okay, by the fact that we're in de Sitter space and the fact that we know we have a particle interpretation that looks pretty good to us in the laboratory, then we know that the moduli in this formalism will just be discrete. There's no moduli stabilization problem because the moduli are actually, following the holographic principle, they live in a fuzzy geometry, and the moduli of fuzzy geometries are just discrete objects. So the continuous moduli that we've seen in string theory and M-theory compactifications come about because of the fact that there we've taken space-time to be infinite in Minkowski, and then in that limit we can make both the compact space as big as we want in Planck units and still have a nice particle physics in our Minkowski space. In a fixed de Sitter space of finite entropy, which we know experimentally, we can't do that. And so in the theory of the real world, the moduli problem of string theory is solved just by the holographic principle. Okay. Yeah, that's all that was said on these transparencies, so I'm sorry for not showing them to you. Yeah, one final note, very important final note. I showed you that in the limit as n goes to infinity, we get supersymmetry back. What is the sort of size of the supersymmetry breaking? Well, it should have to do with n, but remember the supersymmetry we're getting is arising for these individual particles Okay? And those have, if I take a typical state of them, those have ni's which are of order square root of n. Okay? And if you then say that the supersymmetry algebra, in particular this part of the supersymmetry algebra, that P naught, whatever it is, commutes with the Q alphas, is violated at order 1 over square root of n, okay, and you put in Planck units, what you find is that, I mean, this is a dimensionful formula, so I have to put in some units. If you put in Planck units, what you find is that the breaking of supersymmetry, the difference between a particle and its superpartner mass, which, in a theory of gravity, is the difference between a particle mass and the state of one particle plus the gravitino. Okay? That's a mistake one shouldn't make. The real supermultiplets in the theory with spontaneous breaking of supersymmetry are not the original multiplets, but the multiplets formed by the particle plus one, and the particle plus one gravitino. And so that says that M3 halves should go like 1 over square root of n. And in dimensionful units, that's lambda to the 1/4, which is 10 to the minus 2 electron volts. Okay. Now, M3 halves in effective field theory is given by the F over M Planck, and F is what we conventionally call the SUSY splitting squared. And so this gives you an F which is of order 30 TeV squared. And in doing that, I've taken into account this log D factor. Okay? The log D factor makes the effective value of n smaller, so it makes the supersymmetry breaking bigger. And there's a factor of 10 in this formula that comes from saying that log D is of order 10. And I took that from another, and this is just conjecture. Witten argued that the volume of the compact manifold in the right theory of the real world was going to be the thing that explained to us the difference between the Planck scale and the unification scale. So if you put in that phenomenological guess for what log D is, then you get this formula over here. This is a really interesting formula because that's the maximal scale of SUSY violation in any particle multiplet in the world. And therefore, it puts extremely strong constraints on what the low energy theory of supersymmetry breaking is. And I have been investigating that. That is a whole other story and could be the subject of a different set of TASI lectures, but in a different kind of TASI, more devoted to phenomenology. This theory of de Sitter space seems to satisfy all of our prejudices from effective field theory once we renormalize them appropriately. Once we say that, well, you know, when effective field theory tells you something is infinite, maybe you shouldn't believe that infinity. Maybe it's just big. All right? So if you're willing to make the approximation 10 to the 30 equals infinity, then you can say that de Sitter space has an infinite number of horizon volumes. If it's important to you not to make that approximation, and this formula is one of the biggest reasons why it's important, what I'm telling you is that that number, that 10 to the 30th, which is what square root of n is what determines the scale of supersymmetry breaking in particle physics. So taking it equal to infinity is not a good idea. That would lead you back to the Poincare invariant theory you get in the limit as n goes to infinity, and you would have no supersymmetry breaking. And so the world in that limit looks very different from the world that we actually see. Okay, for lack of time, because we have other lectures coming up, I will stop here. I'd be happy to talk to anybody who wants to ask more questions about this. Thank you.